What is a matrix? In simple terms, a rectangular array of numbers enclosed in parentheses or square brackets is called a matrix. For example, F, shown here, is a matrix. It's a rectangular array enclosed in parentheses. The numbers in a matrix are arranged in rows and columns. Matrix F has 2 rows and 3 columns. The first row goes across, row 1. The second row, row 2. The first column, column 1. The second column. The third column. If matrix B has m rows and n columns, then the order of B, also called the size of B or the dimensions of B, is read as m by n. Therefore, matrix F is a 2-row, 3-column matrix, so it is 2 by 3. Note that F is not a 3 by 2 matrix that would have 3 rows and 2 columns. 2 matrices, matrices is the plural of matrix, are said to have the same order if they have the same number of rows and columns. A matrix that has 1 row and n columns is known as a row matrix. The order of a row matrix is 1 by n. A column matrix has n rows and 1 column, so the order of a column matrix is n by 1. For example, matrix A equal to, parenthesis, 1, 0, -2, 4, is a row matrix with order 1 by 4. Matrix B equal to, parenthesis, 1, 7, 10 is a column matrix with order 3, because it has 3 rows, by 1, because it has 1 column. The individual numbers that make up a matrix are called the entries, or elements of the matrix. A matrix with m rows and n columns has m times n entries. Matrix F has 2 rows and 3 columns, so it has 2 times 3, or 6 entries, which you can easily count here. Since it is often necessary to manipulate a matrix or perform algebraic operations on a matrix, you need to become familiar with notation that can be used to represent a matrix symbolically. Matrix notation. In general, a matrix A with m rows and n columns has the form A equals, parentheses, A with subscripts 1, 1, A, 1, 2, and so on, where 1 is the row and 1 here is the column. The second row has notation A sub 2, 1, A, 2, 2, and so on, down to as many rows as you have, in this case m rows. The double subscripts are used to indicate the position of the entry in the matrix. The notation A sub ij indicates that the entry appears in the ith row and the jth column. For example, A21 is the entry in row 2, column 1. We will frequently use the notation A equals parenthesis A sub ij, close parenthesis, to denote a matrix A with entries lowercase a sub ij. Notice the parentheses. Be careful and don't confuse the notation parenthesis A sub ij, indicating a matrix that has I rows and j columns, with the notation lowercase a sub ij with no parentheses, indicating a single entry in matrix A that is located in row I, column j. The following examples illustrate this notation. Matrix G is defined as follows. G equals the matrix with the first row 2, -4, 1, second row 3, 0, 7, third row 14, 6, 5. G is a 3-row by 3-column matrix. Use the matrix to find the following values. G sub A, B equals 7. What are the values of A and B? The only entry in the matrix with a value of 7 is in row 2, column 3. So A equals 2 and B equals 3. A is row 2, B is column 3. The second example, G of sub CD equals -4. What are the values of C and D? -4 is in one position in the first row, second column. So the first row is the first subscript C equals 1. The second column would be the second subscript D, which is 2. So C equals 1 and D equals 2. The 3x3 matrix A equals parenthesis A sub 3, 3 is defined by A sub ij equals I minus j plus 1 for I and j both ranging from 1 to 3. Display matrix A. Again, we'll write matrix A with its general subscript notation. A has 3 rows. The first row, first column entry is A11, then A12 as we go across row 1, A13. For the second row, our first entry in the subscript would be a 2, second row, first column, A sub 22, A sub 23. In the third row, we have A sub 31, and all the first entries here will be 3s, A32, A33. So let's look at this Aij notation. We're told that Aij is equal to I minus j plus 1. So the entry with the subscripts 1, 1 equals 1 minus 1 plus 1 equals 1. For the A12 entry, I is still 1, j is now 2, plus 1 equals 0, and so on. The A13 entry then would equal -1. We move to the second row, A21. In this case now I is 2, minus 1 plus 1 is equal to 2. And continuing with A22, that is equal to 2 minus 2 plus 1 equals 1. And A23 to end the second row would be a 0. For the third row, A31 is equal to 3, A32 is equal to 2, and A33 is equal to 1. and we put them in our matrix A where they belong. The first row is 1, 0, -1. The second row, 2, 1, 0. The third row, 3, 2, 1. How to transpose a matrix. The transpose operation applied to a matrix A simply interchanges the rows and columns of A. The transpose of matrix A results in a new matrix denoted by A raised to a t power. T is the superscript. This operation is one that is quite important in application problems, as you will see in upcoming lessons. To help you understand how the transpose operation works, consider the following example. Let matrix P be defined by P equals, in the first row, 2, 3, 7. In the second row, 1, 4, -6. A new matrix, P transpose, is created by interchanging rows and columns of P. So P transpose equals, P is a 2-row by 3-column matrix. The first row of P is 2, 3, 7. That becomes the first column of P transpose. The second row of P, 1, 4, -6, becomes the second column of P transpose. P equals 2, 3, 7, 1, 4, -6, reading across the rows. P transpose, if you read down the columns, reads 2, 3, 7, 1, 4, -6. So we interchanged rows and columns. We observe that in this example, P is a 2 by 3 matrix. Note here that P transpose has the order 3 rows, 2 columns, so P transpose is 3 by 2. This is not a coincidence. In general, if a matrix A is an M by N matrix, then the transpose of A transpose, is an N by M matrix. Let's look at an example problem. In this example, we want to find A transpose and X transpose, where A is the matrix 1, 0, 4, 2 in the first row, 8, 5, 3, 1 in the second row, 4, 7, 6, 9 in the third row. To find A transpose, we will take the first row and make it the first column. 1, 0, 4, 2. The second row becomes the second column, 8, 5, 3, 1. The third row becomes the third column, 4, 7, 6, 9. Matrix X is equal to the column matrix 4, 1, 5, so that X transpose becomes a row matrix 4, 1, 5. A is a 3 by 4 matrix, and A transpose is a 4 by 3 matrix. Matrix X is a 3 by 1 matrix. Matrix X transpose is a 1 by 3 matrix. When transposing labeled matrices, you must not only interchange the rows and columns of the matrix, you must also interchange the row labels with the column labels. Example, let L be a labeled 4x4 location by size matrix that represents the inventory of LCD flat panel TVs available in warehouses in 4 cities: Roanoke, Richmond, Charlotte, and Atlanta. The rows are labeled by the cities. The columns are labeled by the size of the TV. So it's location by size, and we call that matrix L. To create L transpose, you must not only interchange the rows and columns of L, you must also interchange the row labels with the column labels. Recall that we have L equal to location by size. So L transpose has to be size by location. Okay. The row headings become the column headings as the numbers change. The column headings become the row headings so that they now match the numbers. So this is L transpose.
In matrix operations, the process of multiplying a matrix by a number is often referred to as scalar multiplication, since scalar is just another name for number. When an m by n matrix A is multiplied by a scalar S, the resulting matrix is an m by n matrix with entries that are obtained by multiplying the entries in A by S. Formally, the definition of scalar multiplication is: let A be an m by n matrix, and let S denote a scalar. The scalar multiple S times A is the m by n matrix whose entry in row I and column J is S times A sub ij. The following example illustrates this process. Let A be defined by the following matrix. Find 5 times A. Matrix A is a 3 by 2 matrix with entries in row 1, 2, 1, in row 2, 0, negative 4, in row 3, 1, 3. Therefore, 5A is equal to 5 times the matrix A, 2, 1 in row 1, 0, negative 4 in row 2, 1, 3 in row 3, which is equal to, by definition, 5 times 2 for the first entry, 5 times 1 for the second entry in row 1, 5 times 0 for the first entry in row 2, 5 times negative 4 for the second entry in row 2, 5 times 1, and 5 times 3 for the row 3 entries. Now we do the multiplication and get 10, 5 for row 1, 0, negative 20 for row 2, and 5, 15 for row 3. Notice that matrix 5A is also a 3 by 2 matrix with entries that are 5 times the corresponding entries in matrix A. As with most mathematical operations, there is a set of rules or properties that describes exactly how scalar multiplication can be applied. Matrix operations involving scalar multiplication can often be made easier by using these properties. Properties of scalar multiplication. Let A and B be M by N matrices, and S, S sub 1, and S sub 2 be scalars. Property 1. S times matrix A plus S times matrix B is equal to S times the sum of matrix A plus B. Property 2. S sub 1 times matrix A plus S sub 2 times matrix A is equal to the sum S sub 1 plus S sub 2 multiplied times matrix A. And property 3, S sub 1 times S sub 2 times A is equal to the product S sub 1 times S sub 2 times matrix A. You will learn how to use matrix addition and property 1 in the next lesson. The following examples demonstrate the use of properties 2 and 3. A department store chain sells bed linens to fit twin, full, queen, and king-size beds. They sell sheet sets, designated by SS, quilts, designated by Q, blankets, designated by BL, bedspreads, designated by BS, and bed and bag sets, designated by bag, for each size. The prices in dollars for these items have been organized into the following labeled 4x5 bed size by product matrix, since the row labels give the size of the bed and the column labels give the type of product. Notice that row 1 gives the prices for twin size sheet sets, quilts, blankets, bedspreads, and bed in a bag sets. The second row gives the prices for full size, the third row for queen size, and the fourth row for king size. Part 1. The state sales tax rate in your state is 5%. The selling price of the linens is shown in matrix L. The sales tax is calculated by multiplying 0.05 times L. The total purchase price is the selling price plus the sales tax, or L plus 0.05 times L. By property 2 and the properties of scalar multiplication, we know L plus 0.05 times L is equal to 1 plus 0.05, that quantity multiplied times L, or 1.05 times L. If we set this up in matrix multiplication, we have 1.05 times L, which we rewrite as 1.05 times the matrix L. We then multiply 1.05 times every entry in L, and we get a new matrix that gives the purchase price for each of the items, including the sales tax. How much does it cost, including tax, to purchase a twin size quilt? If we look at the row for twin size and go across to the quilt item, we find that it costs $105 to purchase a twin size quilt. How much for a king size bedspread? If we go to the king size row and go to the bedspread column, we find that it costs $183.75 to purchase a king size bedspread. Part 2. The store is having a sale. For the sale, the selling price of all linens is reduced by 40%. Since the regular price of the linens is reduced by 40%, the sale price of the linens is 60% of the regular price, or 0.60 L. The sales tax is calculated by multiplying 0.05 times 0.60 L. Therefore, the total purchase price is 0.60L plus 0.05 times 0.60L. By properties 2 and 3 of the properties of scalar multiplication, 0.60L plus 0.05 times 0.60L is equal to 0.60 plus 0.05 times 0.60, that quantity multiplied times matrix L, which gives us 0.63 times L. We calculate the multiplication the same way that we did before. 0.63 times L, which we change into 0.63 times our matrix L. We complete the multiplication multiplying every entry in L by 0.63, and we get a new matrix, which is the sale price of each of the linens, including sales tax. Again, all the twin size entries are in row 1, full are in row 2, and so forth. What is the total purchase price, including sales tax, for the twin size quilt and the king size bedspread at the sale price? So our twin size, if we come across twin to quilt, we find that the sale price, including sales tax, is $63. And in the king row, we look until we find the bedspread column and find that the king bedspread price is $110.25. When working with matrix application problems by hand, it is fairly easy to write a label for each row and column. If you are using technology, however, at times physically attaching a label to each row and column in a matrix is difficult or impossible. Matrix addition. Definition. Let A and B both be M by N matrices, where A is equal to the matrix with entries A sub ij, and B is equal to the matrix with entries B sub ij. The sum A plus B is the M by N matrix C with entries C sub ij, obtained by adding corresponding entries of A and B. That is, C sub ij is equal to A sub ij plus B sub ij. Notice that the definition of A plus B requires that A and B have the same number of rows and columns. For example, if A is 3 by 2 and B is 5 by 6, then the sum A plus B is not defined. Example. Find matrix P where P is equal to 3 times R plus 4 times S, and R and S are 2 by 3 matrices with R equal to, in row 1, 1, 2, negative 4, and in row 2, 0, 1, negative 5. S is equal to 2, 2, 1 in row 1, and negative 4, 0, negative 1 in row 2. So P is equal to 3 times matrix R plus 4 times matrix S, which will give us P is equal to 3 times 1 is 3, 3 times 2 is 6, 3 times negative 4 is negative 12, and 3 times 0 is 0, 3 times 1 is 3, 3 times negative 5 is negative 15, which gives us the values of 3 times R, plus for 4 times S, we have 4 times 2 is 8, 4 times 2 is 8, 4 times 1 is 4, 4 times negative 4 is negative 16, 4 times 0 is 0, 4 times negative 1 is negative 4. Now we add the entries and we get in row 1, 11, 14, negative 8, and in row 2 we get negative 16, 3, and negative 19. Notice that P is also a 2 by 3 matrix. If matrices A and B are both M by N matrices, then it is also possible to perform matrix subtraction. The process of subtracting one matrix from another matrix of the same order involves the combination of matrix addition and scalar multiplication. Matrix subtraction. Definition. Let A and B both be M by N matrices, where A is the matrix with elements A sub ij and B is the matrix with elements B sub ij. The difference C equals A minus B is found by adding matrix A and the scalar multiple negative 1 times B. That is, C equals A minus B, which is equal to A plus negative 1 times B, where C is the M by N matrix, C with elements C sub ij, whose entries are C sub ij equals A sub ij minus B sub ij. Example. Find matrix C where C is equal to A minus B. A and B are 3 by 2 matrices defined by A in row 1 is 1, 4, in row 2, negative 2, 7, and in row 3, 6, 9. B is in row 1, 6, negative 1, in row 2, 7, 2, and in row 3, 1, 0. We're finding C is equal to A minus B, so matrix A plus negative 1 times matrix B gives us C equals 1 plus negative 6 in the first entry. The row 1 column 2 entry is 4 plus 1. Row 2 we have negative 2 plus negative 7. The row 2 column 2 entry we have 7 plus negative 2. In the row 3 column 1 entry we have 6 plus negative 1. And in the row 3 column 2 entry we have 9 plus 0. Completing the calculations gives us negative 5, 5 in row 1, negative 9, 5 in row 2, and 5, 9 in row 3. As expected, C is a 3 by 2 matrix. Example. A is a 4 by 4 matrix and B is a 2 by 4 matrix. Is A times B defined? If so, what is its size? A times B is equal to 4 by 4 times 2 by 4. The inner dimensions do not correspond, so therefore AB is not defined. Is B times A defined? If so, what is its size? B times A is equal to 2 by 4 times 4 by 4. This time the inner dimensions agree, both are 4, therefore the product exists and the outer dimensions give us the size B times A is 2 by 4. The previous examples should lead you to 2 conclusions. The order in which the matrices are written when performing matrix multiplication matters, and matrix multiplication is not commutative. In general, for matrices A and B, the product A times B is not equal to the product B times A. You now know how to find the product of a 1 by n row matrix and an n by 1 column matrix. You also know how to determine if it is possible to multiply two matrices and can find the size of the resulting matrix when two matrices are multiplied. In the remainder of this lesson, you will learn to apply your knowledge and perform matrix multiplication. Matrix multiplication. Let A equal the matrix with elements A sub ij be an M by n matrix, and let B be the matrix with elements B sub ij be an R by S matrix. If n is equal to R, or the inner dimensions equal, then the product A times B equals C is the M by S matrix whose ijth entry is defined by C sub ij equals A sub I1 times B sub 1j plus A sub I2 times B sub 2j, continuing in the same manner until we end with plus A sub in times B sub nj. If n is not equal to R, then the product A times B is not defined. Example. Find the product C equals B times A when A and B are defined by A is equal to, in row 1, 3, 1, negative 4, and in row 2, 2, negative 2, 0. B is defined by negative 1, 5 in row 1, negative 3, 7 in row 2, 6 and 4 in row 3. First, let's put the matrices side by side in the order they will be multiplied. So C is equal to B times A, so we put matrix B with matrix A. Matrix C is 3 by 3 since a 3 by 2 matrix times a 2 by 3 matrix, inner dimensions correspond, so we know the multiplication is possible, and the outer dimensions tell us that the result is 3 by 3. Therefore, B times A equals C with entries as shown. We're going to be calculating the entries of C. In row 1 of C, C11 uses row 1 of B and column 1 of A. Therefore, C11 is negative 1 times 3 plus 5 times 2 for a value of 7. C12 uses row 1 of B and column 2 of A. C12 is negative 1 times 1 plus 5 times negative 2 for negative 11. C13 uses row 1 of B and column 3 of A. C13 is negative 1 times negative 4 plus 5 times 0 for a value of 4. Moving on to row 2 of C, C21 uses row 2 of B and column 1 of A. C21 is negative 3 times 3 plus 7 times 2 gives us a value of 5. C22 uses row 2 of B and column 2 of A. C22 is negative 3 times 1 plus 7 times negative 2 for a value of negative 17. C23 uses row 2 of B, column 3 of A. C23 equals negative 3 times negative 4 plus 7 times 0 for a value of 12. In row 3 of C, we have C31, which uses row 3 of B, column 1 of A, C31 is 6 times 3 plus 4 times 2 for a value of 26. C32 uses row 3 of B, column 2 of A. C32 is 6 times 1 plus 4 times negative 2 for a value of negative 2. C33 uses row 3 of B, column 3 of A. C33 equals 6 times negative 4 plus 4 times 0 for a value of negative 24. Putting all of this information together in matrix form gives us C equals B times A is the 3 by 3 matrix with 7, negative 11, 4 in row 1, 5, negative 17, 12 in row 2, 26, negative 2, and negative 24 in row 3. Example. We want to find the values of A, B, and C if F is a matrix that is the product of A times B, where A is the 5 by 4 matrix shown here, B is the 4 by 4 matrix shown here. We want to find only the 3 single entries in F in calculating the multiplication. You do not need to complete the entire matrix multiplication to solve this problem. You can selectively compute entries for A, B, and C in this product. If we denote matrix F as F is equal to the matrix with entries F sub ij, then A is located in the F22 position because it is in row 2, column 2 of F, so it's going to use row 2 of A and column 2 of B. Therefore, A, or F22, is equal to 2 times 0 plus 0 times 4 plus 2 times 0 plus 1 times 3 for a value of 3. B is equal to F34 since it is in row 3, column 4 of F. To calculate B, we're going to use row 3 of A and column 4 of B. B, or F34, is equal to 1 times 3 plus 5 times 0 plus 4 times 0 plus negative 4 times 5 for a value of negative 17 for B. C, which is in the row 5, column 4 position of F, uses row 5 of A and column 4 of B. Therefore, C, which is equal to F54, is 1 times 3 plus 4 times 0 plus 4 times 0 plus 6 times 5 for a value of 33 for C. Of course, if you prefer, instead of finding the values of individual entries, you can find the complete product, F is equal to A times B, and then find the values of the entries A equals F22, B equals F34, and C equals F54 in the resulting matrix.
Matrix multiplication that does not convey meaningful information. Suppose A is an M by N matrix and B is an N by P matrix. Because the number of columns in A equals the number of rows in matrix B, it is possible to perform the multiplication AB. In application matrices, however, each row and column is represented by a descriptive label, whether or not that label is explicitly stated. In application problems, for a matrix multiplication AB equal to C to give meaningful information, it must be true that the column labels of matrix A match the row labels of matrix B. The following examples demonstrate how the process works. Example: the prices in dollars of pizza, soda, and salad at 3 local restaurants are summarized in the following table. The restaurants are Pizza Palace, Antonio's, and Luigi's. And pizza, soda, and salad are what the prices are given for. The following table gives the food orders from 3 campus organizations. The organizations are the Math Club, Student Government, and the Rugby Team. Their orders for pizza, soda, and salad. Your task is to determine how much each group would be charged for its entire order at each restaurant. To help you with your task, you will create matrices M and N using the same format that is shown in the previous tables. Matrix M is a 3x3 food by restaurant matrix representing the unit prices for each of the food items. Matrix N is a food by organization matrix representing the number of each food item desired by each organization. You can see that without labels, it can be a little confusing to figure out how to work these. So let's look back at the original tables. Matrix M has rows labeled by food: pizza from the Pizza Palace, from Antonio's, and from Luigi's, soda from each of those locations, and salad from each of those locations. Matrix N has pizza, soda, and salad according to the orders by the Math Club in the first column, Student Government in the second column, and the Rugby Team in the third column. Since M and N are unlabeled matrices, it is extremely important that you keep a record, either mentally or on scratch paper, of what the rows and columns represent. The rows of matrix M represent the type of food. The food items are, from top row to bottom row, pizza, soda, salad. The columns of M represent the 3 restaurants: Pizza Palace, Antonio's, and Luigi's. The rows of N represent the type of food. The food items are, from top row to bottom row, pizza, soda, salad. And the columns of N represent the 3 organizations: the Math Club, the Student Government, and the Rugby Team. It is mathematically possible to perform the multiplication MN since the number of columns of M is equal to the number of rows of N. Completing the matrix multiplication MN gives M times M equal to these numbers. But does the multiplication give you meaningful information? Look at the calculation of the entry in row 1, column 1 position of the product MN. The number value of this entry, 208.82, was calculated as follows: 8.65 times 4 plus 9.10 times 16 plus 9.54 times 3. That equals 208.82. Let's examine the numbers that contribute to the value 208.82 very carefully. The value 8.65 times 4 multiplies the price of pizzas at Pizza Palace times the number of pizzas ordered by the math club. The value 9.10 times 16 multiplies the price of pizzas at Antonio's times the number of sodas ordered by the math club. The value 9.54 times 3 multiplies the price of pizzas at Luigi's times the number of salads ordered by the math club. Therefore, the sum 208.82 has no meaningful interpretation within the context of this problem. In the above example, matrix M is a 3 by 3 food by restaurant matrix, and matrix N is a 3 by 3 food by organization matrix. Even though the multiplication Mn is mathematically possible, and the resulting matrix is a 3 by 3 times a 3 by 3, which gives us a 3 by 3 matrix, multiplying a food by restaurant matrix times a food by organization matrix is not logically possible, since the column labels of M do not correspond to the row labels of N. M times N, food by restaurant times food by organization, is not logically possible. Example. Returning to the previous example, recall that matrix M is a 3 by 3 food by restaurant matrix representing the prices of the food items, and matrix N is a 3 by 3 food by organization matrix representing the number of each food item desired by each organization as follows. Matrix M is 3 by 3, matrix N is 3 by 3, matrix M is food by restaurant, matrix N is food by organization. Recall that it was not logically possible to multiply matrix M times matrix N, since the column labels of M did not match the row labels of N. M times N was M is food by restaurant, N is food by organization. Restaurant and food do not match. Consider instead the matrix M transpose. Here's matrix M. We interchange rows with columns to get the matrix M transpose. Even though the multiplication Mn was not possible, it is possible to find the product M transpose times N. Since M is a 3 by 3 food by restaurant matrix, M transpose is a 3 by 3 restaurant by food matrix. Therefore, 3 by 3 times 3 by 3 for M transpose times N equals 3 by 3, and M transpose times N is a restaurant by food times food by organization, which would equal restaurant by organization matrix. Performing the multiplication M transpose N gives M transpose N equals, this is M transpose, here is N. You multiply row by column. First row by first column gives us the first entry. First row by second column gives us the second entry. First row by third column gives us the third entry, and that takes care of the first row. Multiply the second row times the first column, the second row times the second column, the second row times the third column gives us the second row. Multiply the third row by the first column, the third row by the second column, the third row by the third column completes the third row. To help you interpret your answer, you can write your answer in table format. Pizza Palace, Antonio's, and Luigi's are the row titles. The Math Club, Student Government, and the Rugby Team are the third column titles. It is cheaper for the Math Club and the Student Government to eat at Antonio's if you compare the numbers in each column, but it is cheaper for the Rugby Team to eat at the Pizza Palace because $91.15 is the least amount in that column. Note it is not sufficient that the type of column labels for the matrix on the left match the type of row labels for the matrix on the right. Consider the following table form of the labeled matrices M transpose and N. You want to complete the multiplication M transpose times N. M transpose, we have pizza in the first column, soda, and then salad. And the rows Pizza Palace, Antonio's, and Luigi's. For N, we have Math Club, Student Government, and Rugby Team, pizza, soda, and salad. In order to perform matrix multiplication M transpose times N, it is not sufficient that the column labels on M transpose are foods and the row labels on N are also foods. The column labels on M transpose must be listed in the same order as the row labels on N. Pizza Palace, Antonio's, Luigi's. Pizza, soda, salad, pizza, soda, salad. So they match up. Although it is not necessary to do so to complete the matrix multiplication M transpose times N in this example, in general, rearranging the rows or columns in one or both matrices so that the column labels and row labels correspond might be needed before you can perform the desired matrix multiplication.